So let's talk about connecting two of the universe's biggest mysteries, the human brain and the totally bizarre world of quantum mechanics. What happens when the most powerful computer we know, the one that's literally inside our heads, meets a brand new kind of computation that could change, well, everything? Let's find out.
Our brains, with their billions and billions of neurons firing in these beautiful, complex patterns, they really are the final frontier of science. But what if the secret to cracking that code doesn't come from building bigger and bigger classical computers? What if the answer lies in a completely different kind of computation, one that plays by the fundamental and, let's be honest, super weird rules of the universe itself?
Okay, so we're going to dive right into a really recent breakthrough in what are called brain-computer interfaces, or BCIs. And this isn't just some theoretical what-if scenario. This is a real-world result that gives us a peek into a radical new future.
Just imagine, for a second, a computer that could listen to all the noisy, chaotic electrical signals buzzing around in your brain, your EEG waves, and understand what you're intending to do with almost zero errors. Think about what that would mean for medicine, for communication, for just human potential. It sounds like something straight out of science fiction, doesn't it?
Well, this isn't a prediction. It's not a dream. That is a direct quote from a scientific paper. Researchers have actually built a hybrid quantum model that can classify complex brain signals with a staggering 99% accuracy. To put that into perspective, that kind of performance just leaves the traditional methods we've been using completely in the dust.
Okay, so a 99% accuracy rate? How in the world is that even possible? To get our heads around that, we need to quickly open up the quantum toolkit and look at the fundamental principles that make these quantum computers so incredibly powerful. First up, superposition. A normal computer bit, right? It's like a light switch. It's either on or off, a 1 or a 0. Simple. But a quantum bit, or a qubit, is way more like a dimmer switch. It can be a 1, it can be a 0, or it can be a blend of both, all at the same time. This one little difference is the first key to unlocking a whole new universe of computational power.
Next is entanglement, the thing Einstein famously called spooky action at a distance. And honestly, he wasn't wrong. When you entangle two qubits, they become linked. They form a single system. If you measure one of them, you instantly know the state of the other one, even if it's on the other side of the galaxy. It's this deep connection that lets you do incredibly complex information processing that's just impossible in our classical world.
And finally, we've got interference. So because these quantum states act like waves, their probabilities can basically crash into each other. Quantum algorithms are designed in this really clever way where the paths that lead to the wrong answers all cancel each other out, while the paths to the correct answer get amplified. It's like a super powerful searchlight that only focuses on the right solution.
So we've got our core principles: superposition, entanglement, and interference. Now let's see how these really weird concepts become the actual building blocks of a quantum computer.
The crucial difference really comes down to the bit versus the qubit. A classical bit holds one piece of information. That's it. But a qubit, thanks to superposition, holds exponentially more. And here's the wild part. For every single qubit you add, the information capacity doubles. We're not talking about a little bit more power. We're talking about an exponential explosion of processing potential.
And creating that spooky entanglement isn't magic. It's just really, really precise engineering. You can think of these quantum gates as tiny little operations that tell the qubits what to do. In just 2 steps, scientists can use one gate, a Hadamard gate, to pop a qubit into that both states at once superposition, and then use a second gate to link it to another one, creating that powerful entangled connection.
Now, for a quick reality check, the physical qubits that we actually build are incredibly fragile. The tiniest disturbance from heat or even a vibration can totally wreck their quantum state. So what engineers do is they use something called quantum error correction to bundle a bunch of these fragile physical qubits together to create one single, much more stable logical qubit. And that's the one we can actually use for reliable calculations.
Okay, now that we have our quantum toolkit all sorted out, let's circle back to that incredible brain-computer interface paper and see exactly how they pulled this off.
Their secret sauce is a hybrid model called QSVM-QNN. The best way to think of it is like a 2-part quantum dream team. The first part, the quantum support vector machine, or QSVM, is like a detective. It sifts through all that messy brainwave data to find hidden patterns.
Then, the second part, the quantum neural network, or QNN, takes those patterns and makes an incredibly accurate decision. It's that 1-2 punch of pattern finding and decision-making that makes it so powerful.
And the result of all this? An accuracy of 0.990. Just let that sink in for a moment. That means, on a standard dataset, this hybrid quantum approach could correctly classify brain signals 99% of the time. That number, it really does speak for itself.
And if you need to see it to believe it, here's the proof. On this chart, you can see the performance of a traditional classical model over on the left. It does okay, right? In the middle, a standalone quantum model does even better. But then look all the way to the right. That's our hybrid model, combining two quantum approaches. It achieves a level of accuracy that is simply in a league of its own.
Now, this one paper is amazing, for sure, but it's part of a much, much bigger story. The entire field is moving away from single experimental processors toward a future of powerful, interconnected quantum systems.
And this isn't just some academic dream. The tech giants are all in. This quote from IBM fellow Jay Gambetta lays it out plain and simple. The goal is to build and network large-scale, fault-tolerant quantum computers within this decade. We're talking about the birth of an entirely new tier of computing.
So let's look at this roadmap. Right now, we're at the stage of these small lab-scale processors, but the ambition is absolutely huge. Within just 5 years, the goal is to be running computations with tens or even hundreds of thousands of qubits. And by 2030, we could see the very first proof of concept of these machines being linked together, creating a distributed quantum network. The pace of this innovation is just breathtaking. We started with this immense challenge of decoding the human brain. We've seen how a new kind of computing, born from the very fabric of reality, is already taking these incredible leaps forward. And it leaves us with one final thrilling question. If we can start to unravel the mind, what other problems we once thought were unsolvable, in medicine, in material science, in our understanding of the universe itself, will finally be within our grasp?